So in this latest video looking at logarithms and exponential, we'll be focusing on curve fitting, and just a warning, this is a very long video. Now when plotting equations like y equals ax to the power of n or any polynomial term, and y equals kb to the power of x, which is like an exponential term, it may be difficult to read values from the curve because as x increases, the range between the y values gets bigger and bigger. So as you can see in terms of these two graphs, so the first graph is where we're looking at a polynomial graph, and as you can see that our y scale, if you can see, if your eyes are good enough, going up in hundreds. So you can see that as x increases, I'm really going from x from 0 to 20. You can see that if I was to read up any value of x, which really won't be a problem, but any extreme value of accuracy with regards to y ordinates is going to be very, very difficult. And as x increases, it's just going to make reading off the y ordinates just a little bit more complicated. And then similarly with exponential graphs, so where you've got kb to the power of x, where k and b are just constants. So with an exponential graph, you can see that as x increases, even in small increments, that the values of y are massively going to be different to each other, and the range of those values is going to be difficult, making it again very difficult to read. And so when you are plotting this type of graph and you want to read information from it, it's really important that you make it appropriate to the values that you are actually going to be using it for, to make it easy for you to read, which obviously is going to be difficult if the values that you are, or if the relationship between the x and the y variables are exponential or polynomial. Now by using logarithms, we can convert some curved graphs into straight lines, and in particular equations in the form of y equals ax to the power of n or y equals kb to the power of x. Now we're just looking at equations that follow that particular format, so we're not looking at, let's say, cubic polynomials, or where you've got a mixture of cubics and you've got a mixture of, let's say, squares, or just based to the degree of 1. And also for exponential graphs, we're just looking at single term graphs of either polynomial nature or of an exponential nature. Now in theory, logs to any base may be used, but in practice you would only use those easily available to you on your calculator. Now depending on which calculator you've got, if you've got the Casio FX991EX calculator, then that gives you a button where you can actually choose your base of your log that you're actually going to be using. So what you find is that there is a button that looks very similar to something that looks like this. Now if that's the case, then you can actually pick and choose any base you want, but typically on much older calculators you tend to find, or more traditional scientific calculators, they just have a simple log button, in which these two I would recommend that you use to the base of 10. So when you are raising things to increase, or taking the log of both sides, then I strongly recommend that you use base 10, or just go with that whatever button your calculator is using. Now an alternative that is to instead use natural logs, which again you're just using your ln button or your ln button, in which then you don't have to worry about entering the bases, and again either or is going to be absolutely fine. So when you're taking the logs of both sides of the equation, you can either use your designated log button, in which all you then need to do is just make sure that you're incorporating log 10. If you've just got a simple log button, that's already going to be pre-programmed to base 10, or an alternative is you just use the ln button. Now when it comes to converting a polynomial term equation into a linear curve, which is what we're going to be focusing on here, what you need to do here is, now a and n are just going to be constants. Now in some cases it might be constants that you're given, or maybe constants that we don't know, but typically speaking they're constants that you're actually going to need to find. So what we need to do is, to get from this stage to, let's say, step 1, is what you're going to do is you're going to take logs of both sides. Now again, as mentioned previously, literally a minute ago, I would say take the log of base 10, or just use your log button. Alternately, what you can use is you can use your ln button function, I should say. Then to get from this stage to this stage, what we then do is, using the laws of logs, we split up the right hand side. So again, basically this is a times x to the power of n, and when you're multiplying or got a product of two terms where you're taking the logs, you can split up into two additions, or the sum of those two things. And then to get from this step to this step, all we're doing here is move the power n to the front. Now, once you've got this, what we then can do, and let me just highlight that. So this is our linear equation. I'm not doing a very good job in terms of highlighting. So we've gone from our polynomial term to now our linear equation. Now, if you're going to plot this on a graph, so rather than plotting our original equation, which is, again, we just write the original, and this is our linear log version of the equation, is what we then do is plot log x against log y. So rather than plotting y against x, which is what we would do in our original equation, what we do instead is we'd scrap y, and instead we're going to plot log y, and instead of using x, we're going to use log x. And once you've done that, what we're then going to do is plot this equation. So this would represent our y, log a would represent our c, which is our y-intercept, and n log x, well, this would represent, well, log x would represent our x value, and n, and again choosing an appropriate colour that we've not used, give it pink, and so here n would equal our gradient, and there would be our linear equation. So that's what we would then plot. Now, plotting each of those again, so this would be our, this point here would be my log a value, and the gradient of that would be my n. So obviously we need an equation where we've got log y, log x, where a and n are constants. And so they would typically be the two values that we need to find. And we can use this linear graph to then find out what those values are for then us to then substitute back into that original equation. So then moving on to a exponential graph. So again, looking at our original equation, which is this here. So this is our original equation. And again, what we're going to do is we're going to take the log of both sides. So take the log of both sides. And just like before, we then split it up. So split up the right-hand side using the laws of logs. And then all we then need to do is then move the power to the front. And just put x to the front. And lo and behold, you've now got your linear equation. So this here is my linear equation. Now, breaking this question up, so unlike last time where if we had a graph and typically we'd be plotting y against x, here when we've got an exponential graph, instead we're still going to stick with x, which is still fine. So we're still going to use the x values, but instead of using y, we're going to use log y. So what you're plotting is you're plotting x against log y. Now from this particular equation, what we've got is log y would represent our y values. A, just like before, would represent our y-intercept, which would represent our c. X is our x. But this time here, that log b would be your gradient. So if you then go on to plot plot x against log y, in which hopefully you'd get a straight line, then this value here would represent my log a value, and the gradient of that green line would give me my log b value. And then once I've got what log b is, I can then use the rules of logs to work out what the value of b is going to be, and likewise with regards to a. So once you've got those values as a decimal, so for example you may end up with, let's say, log a equals, I don't know, 0.25, then all you then need to do is basically do the reverse of that. So if I do that to log 10, then basically a equals 10 to the power of 0.25. If log b was equal to let's say 2.7, so let's say log b equals 2.7. I read that from basically working out the gradient of up against across. then all I need to do is log 10b equals 2.7, and using the rules of logs, and that would be 10 to the power of 2.7 would equal b, and I would have my respective b values. So from that I can then work out what each of these values are going to be. So moving on to our exponential version, so here we've got our original equation, which is going to be in the form of y equals kb to the power of x, where again k and b are just constants. So this here is our original equation, and what we do then is we take the log of both sides. So take log of both sides, and then once we've done that, we can then use the rules of logs. So use the rules of logs and split up the right hand side, and then from there what I can then do is move the power x to the front. And what you've got then is you've got this exponential graph that you've now converted into a linear equation, and this is something there that we then need to work on to find the values of the constants of k and b. So typically when we have a graph, and again typically I'll plot x against y. Now here to work out what the constants are, because obviously it's going to be very difficult to find out what those constants are, instead I'm going to keep my value of x, but instead of using y I'm going to use log y instead. Now once we've got our equation into this form, we've then got it in the form of something that can be represented by y equals mx plus c. So here this is my y value, log k is my c, which is the y-intercept, x is my x value, and here log b would be my gradient. So if I was wanting to find the values of basically k and b, then to find the value of k, well first of all from my graph that's plotted against x against log y, then this value here would be log k. So if let's say log k was, let's say 2.4, then I could use the rules of logs to find out what the constant of k is going to be. So again, if working in base 10, I've got log to the base 10k equals 2.4, which then equals 10 to the power of 2.4, gives me my value of k. I'd enter that in my calculator and I've got the value. Now to work out the gradient, well that's going to be the work out the gradient of that line. So this here, so the gradient is going to be equal to log b. So again, if I worked out that the gradient was, let's say 1.6, then log b would equal 1.6. So log 10 to the b would equal 1.6. So 10 to the power of 1.6 would equal b, and then there I've worked out my constant of b. And once I've got my k and my b values, I can then go back to my original equation and write down what those values are going to be. Now typically speaking, what will happen in a typical question relating to curve fitting is you will be given one of these two formulas. So the first side looks at polynomial equations, or polynomial terms I should say, and the second side looks at exponential. Now typically you'll be asked to find, you'll be given that the let's say a situation follows either one of these two formats. You'll be given the respective formulas. Now the letters might be different. So for example, with the polynomials you might have y equals kx to the power of t, or for the exponential ones you could have y equals j f to the power of x. So letters might be different, but the same format applies. So with the polynomials, your unknown will be the base. With an exponential, your unknown will be a power. Now, typically speaking, you'd always be given x or y data, and again, those letters might change. It's only respective to these two particular examples. So, for example, if I just make up some random numbers for my x, so let's go for 2, 4, 6, 8, and I do the same for the second side, 2, 4, 6, 8, and I just make up some random y values. So again, I'm just going to go for 10, 20, let's go for 60 and 100. I'll do the same for the other side, so let's go for 10, 20, 60 and 100. Now what I'd need to do before I start moving into taking log of both sides, I'm going to have to convert each of those bits of data. So for example, working with the polynomial one, what I'm going to do is I need to work out what, rather than working with x and y, I need to work with log x and log y. So to work out this value here, I'm going to do log of whatever the x value is, so that'll be log 2. This value here would be log of 4. This value here would be log of 6. And this value here would be log of 8. And again, each of those bases could be to whatever base you want, as long as you're using the same base for both your x and your y values. Now for the respective y ordinates, this would be log of 10. This would be log of 20. And again, where I'm getting these values are just from these numbers here. And this third value would be log of 60. And this value here would be the log of 100. And from this, what I would then go on to do is from this table, I would then go on to plot log y against log x on their axes respectively. And hopefully that would produce some form of straight line. Now the key thing to remember is that when you are substituting, when you have converted these xy values into their log equivalents, that your points may not necessarily form a perfect linear line. So what they'll do is you then need to draw a line of best fit, which would then represent your log y equals and then whatever your interpretations are from our previous section. So for example, what I've highlighted in yellow in this screen for the polynomial, and what's highlighted in yellow in this screen for the exponential. And then from that you can then work out what your sort of constants are going to be, either for the y-intercept or from the gradient, and then you then work out what the variables are going to be for your original equation. Now moving on to the exponential one. So again here what we're looking at is the x's are going to stay the same. So here that's just going to be, well, let's use the blue, keep it consistent. So 2, 4, 6, 8. But the y values, I need to use the log value. So that's going to be log of 10. This value here is going to be log of 20. This is going to be log of 60. And the last one's going to be log of 100. And again, the basis doesn't make a difference. It'll be absolutely fine. And again, once I've got that graph, I then want to plot my x against log y. And again, you will find that those points should, if plotted correctly, and if it does follow this model, should produce a linear sort of relationship. And obviously, if you've got a positive linear relationship, then your gradient will be positive. But also bear in mind that you can also have a negative linear where the gradient is going to be negative. So just be wary that not always are your graphs going to have positive gradient. Could also be going down as well, but the format will stay the same. Now the best way of going through this particular topic is to work through a very common example. So looking at this first one, it says that a YouTuber believes that the number of subscribers represented with Y to his channel over time, which represents in T days, can be modeled by the formula of Y equals AT to the power of B. So this here would represent a polynomial because we're looking at T and Y. T would be our X, and T in this particular formula represents a base number. And it says that the number of subscribers is shown in the table below. So here we've got our table, very representative of our X and Y data. Now for part A, it says plot a linear graph to show the data. B is find the values of A and B. And then C is use the model to predict how many subscribers the channel had after 10 days. So let's go about working through this particular question. So working through the answer of, or the solutions for question A, if I just go back to it. So the question A says plot the linear graph. Now in terms of the linear graph, what I need to do, it's not asking me to plot the data that's in this table, because this data is represented by a, well, hopefully what I expect to be a polynomial sort of curve. Just write polynomial. And this is asking me for the linear graph. So what I need to do is I'm going to need to convert the equation into a linear model. And I'm then going to need to convert the table values into the linear variables. And then from this, what I then need to do is then plot this data. So they're the three main steps of what I'm going to do to answer part A. So going back to this then, so what I've got is I've got the equation, I've got my values in this table. So working with this first, And what I need to do is work with that equation. Now, typically this is the equation that you're given. So if I just get a difficult pen, so here we've got for part A, I've got y equals a t to the b. So the first thing I'm going to do is take the log of both sides. So I've got log of y equals log. And again, I'm just going to put that equation into brackets, and there we go. And then what I then need to do is use the rules of logs to break up this right hand side. So I've still got log y equals, and it's going to be log a plus log t to the power of b. Now just make sure the b doesn't look like a 6, because sometimes it can do that. And then finally I've got log y equals log a plus b log t. Now in terms of the actual variables of this particular equation, so log y represents my y, log a represents my c, b represents my gradient, and log t represents my x values. Now when it comes to actually plotting this linear sort of relationship or linear graph, then what I need to do is I need to plot my x data, which in this case is log t, against my y data, which is log y. So what I need to do is create another table, so this time with log t and log y. And I've got 4 values that I need to work the value of, and that's exactly what I'm now going to do. That table's not too bad. Usually there's a lot more wonky than that. So what I now need to do is to find the values of these to then go on to plot them. So what I'm going to do for the first one, so this value here is going to be, now I'm going to use base 10, so I'm going to use log of 10. So this first value is going to be log 10, and it's going to be to the 7 because that's my first value. And again, now the other question is what decimal place and what rounding error am I going to get? Because obviously I'm going to get some quite nasty decimals that I'm going to go for this. Now, what you need to do is recognize what you're going to use these values for. Well, I'm going to use these values to plot. Now, if I write my numbers to 5 decimal places, I'm going to need to pretty much plot to 5 decimal places. So you need to have some form of realization of, okay, what is going to be more feasible for me to plot. Now in an exam, more often than not, the axes will be drawn for you, so you can kind of gauge, right, okay, is it possible for me to plot to 2 decimal places, or do I need to round up to 1 decimal place? You kind of judge your graph based on that. Now typically speaking, I would say go for 2 decimal places, particularly when you're filling in numbers in the table. Then obviously when you move to a graph, you can then decide which is the best option. So for this, it's going to be 0.85. If I type that into my calculator, the second value, it's going to be log 10 of 14, which gives me 1.15. Then I'm going to type in log 10 to the 21, which again gives me 1.32. And then finally log 10 of 28, which gives me a value of 1.45. So these here are my respective log t values. So now what I now need to do is do my log y value. So again, all I'm going to do is take the log of base 10 of these 4 numbers. So for this one, I don't know if I'm going to have enough space inside. I've got the O. So I've got log 10 of 224, and that gives me a value of 2.35. Here I've got log 10 of 1000, which gives me a value of 3. Then here I've got log 10 of 1585. There we go, 1585, in which I get a value of 3.2. And then finally I've got log 10 of 3981, which gives me a value of 3.6. Now, so if I just get a different color highlighter, just because I know red's going to go straight over that, so let's go for blue. And so it's these highlighted values of what I'm now going to plot into a graph. Now remember that I'm going to be plotting your first column, which goes along your x-axis, so it's going to be log t against log y. And what I'm looking for is a linear relationship. So obviously this graph here is going to produce something that looks quite polynomial, whereas with this graph that I've converted it and using these values in this table, hopefully it produces a linear graph. And that's what I'm now going to move on to plot. So once I've completed my converted table of values, I'm going to now reach for my graph and plot the points. Now you should find that, as you can see from the points that I've plotted, now the scale that I've done might be slightly different to the one you may choose, because obviously if you're using graph paper, then yours will be definitely be a little bit more accurate. But remember, whenever you're plotting a graph, you want to try and make it as large as possible, but also make it easy for you to plot. Now, so here we're looking at values of the sort of log t values from 0 to 2, and on my log values, log y values, I should say, I'm going from 0 to 4. And I've plotted my 4 points appropriately. Now, one thing you should notice from where these points are, and hopefully you can see them, if not, let me just accentuate them a little bit by just highlighting where those 4 points are. That what I then want to do is recognize that they do form a linear line. Now obviously it's not a perfect line, but I would say that that does seem to follow a linear sort of relationship, to the point where if this was a scatter diagram, I would say that's very strong correlation, positive correlation. So from this, what I then want to do now is to find my a and b values. Now to do this, what I need to do is draw the line of best fit. Now you can find your a and b values either algebraically or by using this graph, and it's always worth just checking with the question how they want you to work it out. Now if there's no mention of it, then you could use either or, and you might find that if you've gone through all the hassle of drawing a graph, then maybe using the graph might be easier. However, if you're more algebraic and want to try and go for as accurate as possible, you can go for that, and I'll show you both ways of doing it. So in terms of using the graph, here we've got y equals a t to the b, and again what I'm looking for is I'm trying to find the values of b and a, because obviously my y and my t values are the things that I'm plotting. So from this, what we did is we converted this into log form. So we had log y equals log a plus b log t. Now in terms of these values, that log y is my, let's say, sort of y ordinates, and log t are my x ordinates. So all I need to do is find out what log a is, which is the y-intercept. I don't know what I was trying to go for there, so let's just get rid of that. So here I've got my y-intercept, which is log a, and I've got my b value, which is my gradient. Now the first thing I need to do is draw a line of best fit as best as possible. Now with these questions, you might find that your answers might slightly differ to the person next to you, or whoever you're working with, or whoever's on your desk, if there is anyone. Or if you're looking at a textbook or an exam paper, then your values might be different, because obviously you're basing it purely on your graph and where your line of best fit is. Now obviously if you're using computer software, then it would automatically give you the most accurate line of best fit, but we're going to do it purely by sight. So what I'm going to do is I'm going to first of all, now when you're drawing a line of best fit, you kind of want to make sure that you are getting as many points above your line as you're getting above. So all I want to do is try to position this line so that it's as close as possible to all the points. I would say I'm going to stop right there. Now, because obviously that point there is quite close to 3 of the points, although one is slightly a little bit rogue. Now, from this, what I then want to do is find out from my graph what my values of the y-intercept and the gradient are going to be. So for this, I know that, oh, let's colour the lines change colour. So here, this value here is going to be my log a. So from this, I can see that log a is equal to roughly a number that's close to 0.5. And I'm going to work out the value of a. So then if I take the base of, let's say do rules of log on this, so what I've then got, and I'm going to use base 10. So I've got 10 to the power of 0.5 equals a. And if I type that into my calculator, which I'm going to do right now, so 10 to the power of 0.5 gives me a value of around about 3.16, and that's to 3 significant figures. Now the next thing I then need to do, so that's my a value, so that's one of the values found, so I'm just going to put a little box around that. The next thing I then need to do is to find my gradient. Now for this, what you want to try and do is use points where on your graph, it doesn't matter, I'm trying to find the gradient between on the red line, so I'm trying to find points where it fits nicely on the line, where it's easy for me to find the values. So for this, I'm going to go for the values of, let's go for, let's use this point here, which has got the coordinate of 0.7, and it's going to be to 2. And I'm going to use this, and let's find another coordinate that fits nicely onto a point as close as possible. Might struggle, so let's go for this point here. And because obviously I've got the value of that point from my coordinates, I'm going to use it so it goes through the point, and that's got a point of 1.45 and 3.6. So they're the coordinates I'm going to use. So what I'm then going to do is draw my triangle of those points. and work out the gradient. So this distance here is my difference in y ordinates, so that's going to be 3.6 minus 2, which is 1.6. And the difference in the x ordinates, so that's going to be 1.45 minus 0.7, which gives me 0.75. So my gradient value, which is going to be equal to 1.6 divided by 0.75. And if I work that out, of 1.6 divided by 0.75, I get a value of 2.13. So my gradient is equal to 2.13. Now my gradient in this is b, so therefore b equals 2.13, and there is my values of a and b. Now, as mentioned, I did mention that you can find your A and B values by using the graph, or you could do it algebraic, which is absolutely fine. The only thing you've got to bear in mind is that if you are going to do it algebraically, you're going to be using the coordinates that you're getting from your converted log value. So you're going to be using log t against log y. Now the problem is, as you can see from the graph, that those points don't exactly go onto my line of best fit. Now a couple of them are very, very close, but only one of them really does from my line of best fit. Now obviously when you draw a line of best fit, you can use coordinates if the line that you've drawn to represent the line of best fit goes through those points, and that would be absolutely fine. So then you could follow, for example, if let's say my line of best fit went through this point here and this point here. Now this point was, looking back at the table, was 0.85 and 2.35. Oh, don't know where I've gone a bit wayward on that one, so just get rid of that. And 2.35. So from this I could use this as my, let's say, x1, y1, and this value here as my x2, y2, and I could use the formula of that m equals y2 minus y1 over x2 minus x1, and then obviously I can find out what my gradient value is. So my gradient value, this would represent b. Then to find the y-intercept, all I'd do is I'd use y equals mx plus c. Now x and y are basically two coordinates, a coordinate that lies on the line, and the gradient m is your b value, which you've worked out, and then I could rearrange that to find out what c is, and then that would therefore give me the value of log a, and there we go. So c equals log a, and then you can then rearrange your log a to find out what the value of a is, and you can go from there and you've got your value. So it works one or two ways. It all depends on what the points are like on your graph. If it fits nicely, then yes, you can use the actual coordinates and get your answer a little bit more accurate. But if your points are slightly off in terms of your line of best fit, then I would definitely opt for using your diagram. Now, as I mentioned, your values that you get that might be slightly different to what you can read in your exams or in your textbooks in terms of mark schemes. So just bear that in mind, that there is going to be some discrepancy based on what you're doing, and it could affect future answers. Which then leads us on to part C. Now, by using this model, because you are picking values from a particular graph, your graph might be different to, let's say, someone else's, or the type of graph that's expected either in an exam or in a textbook. So you might find that your variables that I've picked here, so for example my 3.16 or my 2.13, might be slightly different to what you may have in your working. And obviously that's going to have a knock-on effect to any future questions. So it's always important that you do follow the model, but not necessarily think that you've got the question wrong. It may be a case of that your variables might be slightly out, which is why you might get a different answer. However, if you were to do it in an exam, you would tend to find that you would still get full marks, because there will be a range of values that they would accept as being correct. So now that I know my values of A and B, so for part C, let's try not write with a rubber. So for part C, I've got the A value of 3.16 and I've got my B value of 2.13, and the original formula was A times T to the power of B. So from this I can then replace these numbers into the formula. So the actual formula is Y equals A, which is 3.16, multiplied by T to the power of 2.13. Now the question's asking me how many subscribers did he have after 10 days. So when T equals 10, all I'm going to do is substitute into this formula. So I've got 3.16 multiplied by 10 to the power of 2.13, and I type that into my calculator, which I'm going to do right now. So 3.16 times 10 to the power of 2.13 gives me an answer of 426.27 blah blah blah. So I would say roughly rounded up it would be 426 subscribers. Now the important thing with this is that you're using the values that you have found from your graph or what you have calculated. Now continuing from this question, it says that a rival YouTuber's channel is losing subscribers. I know that feeling. It says that a number of subscribers to the rival channel is modeled by the equation of y equals 15t to the power of -1. So the question D says write the equation in linear form. So here what we're doing is going straight into writing this equation using logs to write it in linear form. So here let's get a different color pen. Let's go for purple. So for D I've got the equation of y equals 15t to the power of -1. So first thing we're going to do is take log of both sides, in which I've got log and then 15t to the -1. And then break up the right hand side into two sections. So I've got log 15 plus log t of -1, and then move the power to the front, in which I get log t equals log 15 minus log t, because obviously move the log to the front and that's what we get. Now you could obviously write this as log y equals minus log t rather, plus log 15, and that's absolutely fine. Any of those two answers are going to be absolutely fine. And then obviously for part E, it then says plot the linear graph on the same axes as we did for part A. So let's do just that. Now when it comes to plotting the second YouTuber's subscriber list, now the problem is here I haven't got a table of values, but I'm still asked to plot it. Now what we need to do is, well, we know it's going to be a linear relationship, so if I just look at what the equation actually is, so the equation was log y equals, and again just scroll up just to make sure that I'm not going to mess it up. So I've got minus log t, so minus log t plus log 15. Now for this, I'm hoping it's going to be a linear relationship, which is what we've been already assumed that it's going to be. So all I need is 2 points. Now the 2 points I need to do is simply as possible is to find the first one. So when log t equals 0, then all I'm going to left with is basically I'm going to left with log y equals log 15, which gives me a value of around about 1 point, and it's going to be, and just bear with me to type it into my calculator, it's going to be 1.17609. So my first coordinate is going to be at 0 and then 1.7, which is at this point here. Now when log y equals 0, then what I end up is with 0 equals minus log t plus log 15, and again take this to the other side, in which I end up with log t equals log 15, which therefore means that log t equals 1.17609. So that gives me a value that's around about here. So all I now need to do is to draw a straight line going through those 2 points. That's exactly what I'm going to do. So here I'm going to go for this, and again I'm going to try and go for as close as possible as to what I can get, and I end up about there. So there I've plotted my 2 linear equations. Now the next part of that question then said, if we just scroll up to that next part of going back to the question, it says using the graph or otherwise find the day in which the YouTubers had the same number of subscribers. So I'm looking for the YT value of where those 2 points actually meet. So I'm looking for this value here. So this is the point where they had the same number of subscribers. Spell it just about. So it's this point here. So I'm going to say that that point there is roughly, at a guess, now again based on my graph it's not been that accurate, I'm going to say assume it's about 0.22. So here I've got that log t equals, so I'm looking at the time of, I'm sorry, I'm looking for the number of, was it number of subscribers or was it a number of, so on what day, find out which day. So I'm looking at t. If it was number of subscribers, or what day did they have the same, well, how many subscribers did they have the same at the same time, then I'll be looking at log y. So here log t is 0.22. So again, if I'm looking for the same base, so it's log 10 to the t equals 0.22, then I get t equals 10 to the power of 0.22. And if I type that in, 10 10 to the power of 0.22, I get an answer of around about 1.65. And so therefore t is around about 2 days. So after 2 days, that's when they had the same number of subscribers. So then moving on to the latter part, so it says, explain why these models may not be a realistic model over I should say, a period of time. Now, there's several reasons which you could give for this particular example. And again, I'll just explain what this is. Now, when it comes to this, it just really depends on your own interpretation. So here we're expecting, why can our graph of YouTubers in terms of their subscriptions per channel not be followed by this model? Now, I would say that any of these points would be absolutely fine. So the model predicts that the first YouTuber will continue to grow exponentially for years. However, in reality, it is likely that the growth will begin to slow over time. And this is probably due to either competition, so more and more YouTubers, so people are subscribing, will probably find other alternatives. You could also have a decline in popularity, so you might find that there's more intuitive ways of, and channel material might be different, but also it goes to a point where there is always going to be a limit to how many people are actually viewing your video. So it's not going to be something that goes on and on forever. So you could get to a point where it just completely exceeds the number of the human population on the earth. But again, it works in very, very different ways. Now, also the model predicts that the second YouTuber will end up with less than 1 subscriber. Now, again, this is highly unlikely because obviously you're going, the line of the second YouTuber, which is represented by the orange line, does decline quite rapidly. And obviously with time, as t goes, it then goes into negative values. Now, it's not possible for you to have negative subscribers. Now, like I said, I might be doing a good job with my maths channel, but again, it's not possible. And you tend to find that when you get to a point where you don't have that many subscribers, that you either probably give up, or you might find that you reassess your material and you start improving. So again, having a massive linear decline of material or subscribers is unlikely to happen, because either you would just shut up shop or you would change your game and you would try and find other ways to increase the number of subscriptions rather than just simply watch them disappear. So moving on to example 2. So this question reads, the temperature theta in degrees Celsius of a cup of coffee at time t minutes after it is made is recorded as follows. So here we've got a table and we've got the time in minutes has elapsed and going up in 2, 4, 6, 8, 10, 12, and we've got the temperature of that cup of coffee, and it's going from 81 to 70 to 61 to 52 to 45 to 38 degrees respectively. And this first part of the question, it says plot the graph of theta against t, which is really, really important. So it's asking us to plot the actual raw bits of data from that table. Then B then says show how it is possible by drawing a suitable graph to test whether the relationship between theta and t is in the form of theta equals ka to the power of t, where a and k are constants. And then C, carry out the procedure finding the values of a and k. So very, very similar to our first example. However, it's slightly worded a little bit different, and the steps in which we process this are going to be a little bit different. So let's have a go at answering this question. So plotting the data and choosing an appropriate axis, I've got t minutes going along the x-axis and I've got the temperature going along the y-axis. And there I've plotted my sort of 6 points I've been given from the table. Now, what is important is that although it seems and resembles a sort of linear line, the temperature seems to be decreasing at steady rates, that you will tend to find that the graph does follow more of an exponential model, because eventually that cup of coffee will slowly start to turn and stay at room temperature. Because obviously if it does follow a linear model, and you tend to find, or my question might ask you, why does it follow a linear model, is because obviously if you leave that cup of coffee for however long, let's say 30 minutes, it's not going to turn into ice. So it's going to stay at room temperature. And that's where you tend to find that by adding a few more bits of extra data, it will then follow an exponential model. Even though your graph and data doesn't show that, you tend to find that that might be the case. Now, the second part of the question started talking about, if we return to what the question actually asked, it says show how it is possible by drawing a suitable graph to test whether the relationship between theta and time is of the form of theta equals kat, where a and k are constants. So if a relationship is in the form of theta equals KAT, what we could do is take log of both sides. Now for this I'm going to kind of mix it up. Now it doesn't really matter what form of logs you take or what base you're using, as long as you're applying the same base to each side. Now for this question I'm going to use ln and use natural logs and show you how it's no different to when we used actual logs to a base of a particular number. So this I'm going to take ln of both sides. So I've got log theta or ln theta equals ln of ka to the power of t, and then I'm going to split up the right hand side. So I've got ln of k plus ln of a t. Oh no, and then we'll just turn that t into a power. Oh, what's going on there? So let's change that to a power, and then I've got ln theta equals ln k plus t and then log a. And there is my sort of linear model. Now we haven't quite answered the question, so there I've got my linear model. Now from this, this is, as we know, that this is an equation that can be seen as y equals mx plus c. So going from what this says here, that ln of theta is my y, ln of, or m is my gradient, so that's going to be ln a. So this here is my gradient. I've got the letter t, which acts as my x, and I've got ln of k, which acts as my y-intercept. Now this is an equation of a straight line, and consequently if the graph of ln of theta against t is a straight line, then the model theta ka to the power of t is appropriate for this relationship, and that's going to be based on where the gradient is going to be ln a, and if the gradient is ln a, then the value of a is going to be e to the gradient, and if the y-intercept is going to be ln to the k, so therefore k is going to be equal to e, and it's going to be to the power of the y-intercept, whatever that y-intercept may be. So this is hypothetically what my a value and my k value are going to be if the equation is a straight line. So the next part then says for us to find the values of a and k. So what we need to do first is, first of all, use our original tables in our value, in our table, which I will just scroll up, which is here. And I need to convert this working with, now because my variables when I'm looking at my linear model are using t is still the same, but instead of using theta I'm going to use ln theta. So all I need to do is do the ln of these theta values to find out what ln theta is going to be. So gauging an understanding about where these values are, so I need to work out the table of t and ln theta, because they are now my two main variables, replacing what I would class as being my y and my x. So to get the 4.39 value, so let me just tell you where I've got that. So that there is ln of 81. This 4.25 is ln of 70. This 4.11 is ln of 61. And the next one is ln of 52. 3.81 is ln of 45. And 3.64 is ln of 38, and those values I've just put in brackets are ones that were given to me in the original table, so they're my original temperature values. Now if I then go on to plot that graph of theta, ln theta, or t against ln theta, you can see here, and I draw my line of best fit, you can see that those points do model a straight line, so therefore it does prove that the model can be written as a linear value. Now the next thing you can look at, now in the first example I looked at using the graph to find out what my ln k values are. So for this, let's just write down the formula. So the formula for this, if I go back, is going to be ln theta. That's right, ln theta equals, and it's going to be ln k plus t ln a, and I need to find out what these two values are. Now this value here is my gradient, and this value here is my y-intercept. Now obviously what I can then do is, using the graph, I could find out what these values are. So depending on how accurate you are, you can read that value, and also what you can then do is draw your triangle, remembering that it's going to be a negative gradient because obviously the line's going downwards, and I can then work out what my gradient is going to be to work out then what A is going to be. Now from this, so this gradient will equal ln A, whereas this y-intercept value is going to be ln K. And then from that I can then work out what A and K are going to be by taking the E of both sides. Now because the points lie on the straight line, and it doesn't actually tell me in the question that I need to use the actual graph, let's now work at this and do this by using algebra. So from this we can know that the gradient, so if I just write down that all again, so the gradient is equal to ln A. So then using two values from the table, so if I was to suggest that I use, so using, let's go for 2 and 4.39 and 12 and 3.64, that I get that the gradient is going to be equal to y2 minus y1, so it's going to be 3.64 minus 4.39 over 12 minus 2. And if I type that into my calculator, I get a value of minus 0.075, which kind of makes sense because I've got a negative gradient. So that means that ln A is equal to minus 0.075. I need to work out the value of A, so if I take E of both sides, I get E equals, or as I say, E of, let's just rub that out. So if I take E of both sides, I end up with E ln A equals E of minus 0.075. And obviously the E and the ln cancel out, so I've got A equals, and it's going to be E to the minus 0.075. So therefore A equals 0.93, and that's to 2 decimal places. Then looking at the y-intercept, well, for the y-intercept, what I can then do, so the y-intercept, which I worked out to be ln K. Now, if I know that I've got y equals mx plus c, I know that x and y, well, I've just got to pick two coordinates. So using, let's go for 2 and 3.4 and 2 and 4.39 as one coordinate. So this is my x, this is my y. I now know that the gradient is equal to I'll say ln is, the gradient here is, so here we've got ln of theta equals ln K plus T ln A. So from this we know that I'm using 2 as my T value, I'm using 4.39 as my ln theta value, and my ln A value is minus 0.075. So substituting that in, I can then work out what ln K is going to be. So I've got 4.39 equals ln K plus, and it's going to be 2 times 0.075, and that's minus. And I can then work out, that ln K is going to be equal to 4.54. That's to 2 significant figures. Then from this, what I can then do is take E of both sides. So E ln K equals E of 4.54. That leaves me with K equals, and I type that then in, and I get 93.7 to 1 decimal place. And therefore giving me my final formula of being that theta equals 93.7 times 0.93 to the power of t. And there is my final formula. And the reason where that final formula comes from is from theta equals Ka to the t. And all I've done there is just replaced my K and my A values into that formula to give me what the model is going to be.